Waiting for mortgage rates to drop could be a costly mistake. Once rates drop, new home buyers will enter the market and prices will soar even higher. At Churchill Mortgage, you can get a free analysis and learn how to avoid the trap of waiting for interest rates to drop. Buy now and refi later at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591, NMLSconsumeraccess.org, Equal Housing Lender, 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Hello once again. Thanks for joining us on Space Nuts. It's a show about astronomy and space science. And this week we have got a lot on the agenda. It's very telescopic this week. We'll be focusing on, the James Webb Space Telescope. It's in the news again. We'll also be talking about the telescope SOFIA, which is sort of at the other end of its life spectrum, telescopically speaking. And we will be focused on the sun as well, because it could actually be a very helpful tool going forward for our, in regard to looking into space. We've got a question from Rusty in Donnybrook, which is also focused on the James Webb Space Telescope, one about weird radio signals, and a nice little note from Jordan that we want to share with you. That's all coming up on this edition, episode 303 of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me, as he does every week without fail because he's chained to the desk and can't possibly get away, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How's it going today?
Yeah, pretty good. Bit wet. We're getting more showers.
Really?
But the part that worries me is the big cold front that's moving in. We're going to get our first lick of winter in a few days.
Yes.
Not looking forward to that. Already got the Ugg boots on. Can't live without my Ugg boots.
Oh, dear, no.
It's dreadful, isn't it? Judy hates them.
Mine are Ugg too, but they're a bit smaller. So.
Oh, yeah, they're much better, aren't they? Yeah, these things they nearly go up to my knees. We better get on with it, Fred. Now, let's start with a bit of an update on the James Webb Space Telescope. It's one of the hot topics in astronomy at the moment. If you analyse metadata online, this is the number one topic of interest in astronomy at the moment, and not surprisingly because it promises so much. So where are things up to with the James Webb Space Telescope?
It's all good news, actually, Andrew. So, of course, the telescope launched on Christmas Day last year is safely at its observing position, the L2 Lagrange point, about 1.5 million kilometres beyond the Earth in the solar system, on the direction away from the sun. So its mirror is all unfurled, of course, but I guess the recent news is that the telescope's focusing processes, this process of aligning the telescope mirror segments, first of all, and then aligning the instruments that those mirror segments will feed, is complete as of the 28th of April. So that means that the telescope's essentially usable now as an instrument for delivering images. And actually, you don't have to look far on the space.com website to see some of the imagery that's been sent back. And it looks fabulous, Andrew. It looks really terrific from the various cameras. What's in progress now is the next stage, which is cooling the detectors, because being an infrared telescope, the James Webb looks at effectively heat radiation. Infrared is radiant heat, although at the near infrared end there's not much heat in it. It's a large spectrum of wavelengths, which include the idea of heat coming from other objects in space. But you can imagine how much heat you get from a star or a distant galaxy. That's why it's got such a big mirror. But in order to be able to detect infrared radiation, you have to have your instruments cooled in the region of well, 2 or 3 degrees above absolute zero, and some of them are even less than that, as I understand it. So absolute zero, minus 273 degrees Celsius. So that cooling process is in progress. I believe that the MIRI instrument, that's the mid-infrared instrument, is well on its way to achieving that temperature. It's done by really very clever refrigerators that use liquid helium as their refrigerant. We actually use them in ground-based astronomy as well as space-based astronomy. So it's thumbs up on all fronts. And, it's only a month away now, or maybe a little bit more than that, but not too much longer, before we'll start seeing the first science images coming from the Webb.
Yeah, that's really exciting. Can't wait for that. I would have thought it would be a fairly easy process to cool things down in space. It is a pretty cold climate.
Yeah, that's right. And in fact, some spacecraft instruments are what you call radiatively cooled. That means you just cool them by radiating heat into space, paint them black, and that'll do it, and put them out of the light of the sun. But these are active cooling systems that are being used on the Webb, at least on some of the instruments. So it's an easy process. But when you control when you have to control the temperature to within a fraction of a degree, then it's quite challenging. I should say that the reason why you have to do that is that the detectors themselves, of course, are warm. And so if you didn't cool them, they would swamp themselves by their own radiant heat, the infrared that they're radiating, and you wouldn't see anything because it would just be white images. So that's why they've got to be cooled down to get rid of all that thermal noise, as we call it.
It's very technical, isn't it? There's so much to consider. And
yeah, indeed.
I must say I am very impressed with how well this has gone. Touch wood, don't want to put the mocker on them, but I've got to say that everything's just gone swimmingly. Even when they ran into a problem, they had a very easy solution and enacted it very quickly. So it's been a heck of a mission so far. Let's just hope it keeps going that way.
Yeah, it is. It's kind of exemplary. It's exactly what you hope will happen. It's NASA at its very best, which is fabulous.
All right, there'll be more news on James Webb very soon. In fact, when we get to our question segment, we will indeed be answering a technical question in that regard. Now, still on space telescopes, one that I think a lot of people will be familiar with once we describe it is SOFIA. Sadly, though, it's coming to its end of life.
Yeah, that's right. Which certainly for the users of SOFIA is, is very disappointing. So what is it? It is the name is an acronym for the Stratospheric Observatory for Infrared Astronomy. So once again, it's an infrared telescope, which this time doesn't fly in space. It flies in the body of 747 SP, the special performance version of the 747. Which has this whole cutaway in the side of the fuselage, and I think it's about a 2-meter telescope, might be a little bit bigger than that, which 2.5 meter. There you go, which is mounted towards the rear of the 747. The telescope itself weighs 17 tons, Andrew, so it's not a small piece of kit. That's a 2.5 meter telescope, and the idea is that you fill the plane up with astronomers and technical support staff, of course, and fly it up to heights in the region of 12, 13, 14, perhaps even higher kilometers, where you're above virtually all the moisture in the atmosphere, all the water vapor, because the infrared wavelengths that the telescope is looking at are the ones that are absolutely slaughtered by water vapor. In other words, if you put your telescope at sea level, there's so much water vapor in the atmosphere that you don't see anything. But once you get up to those heights, 40,000 feet and above, they are essentially seeing through a clear atmosphere in terms of the water vapor absorption. So it's been very, very productive. I've got a colleague, actually, Stuart Ryder, who's used it several times. I think he's flown on it maybe twice, maybe once. He will be very disappointed because his research essentially needs those infrared wavelengths that SOFIA can see. And it's a little bit controversial because that SOFIA can observe wavelengths that the Webb telescope can't. And it's, the Webb's going to do some marvelous things, but there are frequencies that SOFIA looks at that aren't covered by the JWST. So why is it being closed? Especially being closed down early, because it was originally going to have a 20-year lifetime, but in fact it was only 8 years ago that it was first commissioned. And the answer is it's a cost-saving venture, Andrew, because its operating cost is roughly the same as the Hubble Space Telescope. And that perhaps puts it into perspective. It's roughly $85 million a year, the operational cost, very similar to Hubble. If you compare the number of people who've seen results from Hubble with the number of people who've seen results from SOFIA, that puts it a little bit more in perspective. I should mention, by the way, it's not just NASA that operates SOFIA. It's also the German Aerospace Center, the DLR. So, yes, it's going to be wound up by the 30th of September this year. And it's a sad outcome. I guess it's also a reflection, though, on its priority in that sort of review of astronomy that's carried out. There's one in the United States, one here in Australia, and there are others throughout the world. The decadal surveys, where astronomers are canvassed as to what their future requirements are, what sort of work they want to do. And in last year's decadal survey, SOFIA came out fairly low in its rankings. And that's another reason why NASA and the DLR have together decided to basically to shelve it. I haven't said what it's done, and I'm hoping you're going to say. So what has it done, Fred?
I was about to say, I was going to go down a different path, but that is probably the most obvious thing. We should talk about some of its achievements, yes.
Yeah, and they're pretty spectacular, although, as I said, they're not really in the same league as the Hubble. But perhaps the most famous one is the measurement of the detection of water on the sunlight side of the moon. Water actually locked up in the lunar dust. You and I spoke about this. I guess it's probably a year or so ago, but we certainly gave it a lot of coverage. But another one that's quite prominent scientific result, and I think this is actually the kind of work that my colleague Stuart was involved with, measuring details of galaxies that you can't see in any other way. For example, their magnetic fields, which you measure by looking at the polarization of the infrared light that's coming from them, because magnetic fields, what they do is they align grains of dust along the magnetic fields, and those grains of dust are orientated in a particular way along the magnetic fields. That imprints itself on the polarization of the radiation that's passing through the dust and lets you see the magnetic fields. And SOFIA has been really productive in that region, as well as other science as well. So it has been a very successful venture. But an expensive one, that's the bottom line.
Yeah. One of its lesser-known achievements, Fred, is when it comes into land at its base in California, it gets some really good beach photos, especially in summer.
I believe so.
Pretty impressive.
I was going to say, it also flies from our part of the world as well, from New Zealand from time to time.
Oh, okay. Yeah, that's right. We did talk about that. at one stage. But sort of getting back to reality, reading between the lines in the article that I've got in front of me, there's a lot of sadness behind all this. A lot of people are very, very unhappy that it's coming to an end.
Yeah. Well, always when a facility like this is brought to a close, yes, it's not a happy time. But in many ways, it's a reflection of the world we live in, and that. I suppose frugality with resources is common throughout the whole world of astronomy, because astronomers tend to do things on a shoestring. SOFIA is pretty expensive, as you'd imagine, to cost, to fly an aircraft like that, which needs a crew. It's not like a robotic spacecraft that can sit there and do its own thing with nobody looking after it. It's just a victim, I guess, of not so much cost cutting but of that frugality that I was talking about. Yeah, astronomers want to put their resources where they're going to produce the most science.
What do you think is going to happen to all the hardware, the plane, the telescope itself? What will they do with all that?
I don't know the answer to that.
Garage sale.
It could be a garage sale. Could wind up in a museum.
That's what I was thinking, actually.
Yeah, the telescope itself and the hardware that goes with it has probably got reusable value. It's a significant infrared telescope equipped with state-of-the-art instrumentation. So, yeah, interesting view. A lot of the technology of the telescope, though, is specific to the fact that it looks through a hole in the fuselage of an aircraft. It's got this huge elevation bearing in it, altitude bearing, as we call it, the one that lets the telescope move up and down. An enormous bearing with big structure attached to it. Yeah, be really interesting to see what happens. We might pick up on that story when there's a bit more news on it, Andrew.
I suppose so, yeah. It's just been an amazing project, and probably a unique way of taking observations, and people must be wondering, how can they get a stable image when they're flying at 900 kilometres an hour in the upper atmosphere, trying to point a telescope at something? But they'd have all that covered.
Yeah, they do. Yeah, and a bit of turbulence wouldn't come in handy, would it?
Not really. No.
Some of the stuff that you go through when you're on these long haul flights. Well, just one final comment, which has just come to mind. SOFIA itself wasn't the first of these. It replaced a telescope called the Kuiper Airborne Observatory, the KAO. I can't remember what aircraft that had a hole cut in it for, but it was a different aircraft, a different venture, and SOFIA was the successor to KAO.
Okay, yeah, I'm just trying to find out now what the aircraft was. Looks like it might have been a Galaxy.
That's possible, yes.
Yeah,
it certainly wasn't a 747.
It's a Lockheed Starlifter. There you are.
There you go. There you go.
I knew I'd find it.
I knew you would too.
All right. Well, we will watch with interest as things develop with James Webb and the beginning of the end of SOFIA. You're listening to Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, I've talked in the past about all our social media platforms, and that includes Facebook. It includes, and that is the official Space Nuts page on Facebook and the Space Nuts podcast group. Join both. Doesn't cost any extra. There's also YouTube, and hello to everybody watching on all of those platforms right now, because we do the show live every week, the unabridged version, I think you'd call it. We're on Twitter, we're on TikTok. Yeah, I know. And I don't know where else we are, a few others. But social media is a very important part of our repertoire, and gives an opportunity for people to sort of talk outside of the podcast, so that they can chat to each other and ask each other questions and share photos and whatever they like. It's really good that social media's been able to sort of value add to the podcast. So find us on your favourite social media platform and join the ranks. We'd love for you to be a part of it all. And don't forget to leave reviews on your podcast platforms. We love your reviews. We've been getting a few really good ones lately, so thank you to those people. Now, Fred, let us move on to the next topic, and we're still talking sort of space observation, but this relates to gravitational lensing, which we've talked about before. This trick of the universe that allows you to see things in different ways and sometimes in different time scales. It's a pretty neat trick that they've been able to observe and take advantage of. But now, looks like the sun might be able to help us in this regard. That's exciting.
I think it is too. I love this story because I kind of foreshadowed it nearly 20 years ago in my book, Stargazer, The Life and Times of the Telescope, because that winds up with the idea of a black hole telescope that uses the gravitational distortion of a black hole to form images of very distant objects. So we're not here thinking about manipulating black holes, but thinking about putting a spacecraft in such a position that you could use the gravitational distortion of the sun itself to form an image of a very distant exoplanet up to 100 light years away. So it's not a new idea. I mean, gravitational lensing is, as you and I know, is used throughout astronomy. Usually it's clusters of galaxies that are distorting the space around them in such a way that they magnify the images of more distant galaxies beyond and let you see some of the structure in those distant galaxies and certainly see them a lot brighter than you otherwise would. And in fact, in one case, which we covered recently, a single star in the early universe has been imaged by this gravitational lensing technique. It's fantastic stuff. Uses a huge amount of computing power, as well as the technology of big telescopes looking at these distant galaxy clusters and the even more distant galaxies beyond formed in the gravitational lens. But this idea, which has come about because of several different, pieces of innovation that have been put into it, that really, I think, is the most refined version of this gravitational lensing that we've heard suggested. And the work that we're describing actually comes principally from the Kavli Institute for Particle Astrophysics and Cosmology, or KEPAC, which is at Stanford in the United States. And actually a PhD student in that institution, whose name's Alexander Madurovich, I hope I'm pronouncing it properly, he has basically produced an algorithm that will actually reconstruct the image of a planet in some detail from the gravitational lens, formed by the gravitational lens produced by the sun. Wow! And so what you see when you look at one of these gravitational lenses, what you would see if you could be at the gravitational focal point of the sun, would be a sort of blob of light and light and darkness. But it's the algorithm that you use to turn that into, in fact, you might see a ring actually to start with. The algorithm that you can use that to turn it into an image of the distant planet is the clever bit. And that's really fantastic news because I was not clear that would be possible, but it seems to have been so.
That's rather extraordinary to consider, because up until now, exoplanets have basically been left up to people to create artists' impressions.
Exactly.
So you're really not getting a genuine insight into what these places might look like. But to be able to actually gather an image like they did with that black hole recently, it's not a photo, but it's an image, and construct what would be an accurate portrayal of an exoplanet. That would be incredible.
Indeed, it would. There is a downside to it, though, Andrew.
Aww.
And that is, in order to see this ring of light that metamorphoses into an image of a planet when you put it through the computer system, you've got to be at what you might call the focal point of the sun's gravitational lens. And that's rather a long way away. In fact, 14 times the distance to Pluto is where that is. I'm not going to do the sum in my head. Pluto's about 30 astronomical units away on average. Actually, no, at its nearest, it's about 30. It's rather more than that on average. So 14 times that distance. Now, remember, it took a decade to get the New Horizons, or the best part of a decade, I think it was 9 years actually, to get New Horizons, the fastest spacecraft ever launched, actually, in terms of its launch velocity, to get New Horizons to Pluto back in 2015. So you're talking about, with present technology, of order 100 years. It's a long, long journey to put your detecting spacecraft in the right place in relation to the sun's gravitational lens, but it's not impossible.
Yeah.
And if you used some of the techniques that are being talked about for pushing stars, for pushing spacecraft to the nearest star, that's to say the solar or the light sail technology, that might allow you to shorten that intervening time. However, it's still something that I suspect neither you nor I are going to see come to fruition. But
I'm so disappointed.
Within 40 or 50 years, it may be that, maybe even less than that such a mission will be launched to send a spacecraft to the sun's gravitational focal point. You'd choose a position where you could image, maybe so that you would get lots and lots of stars in the field of view in order to look at their exoplanet potential. It's another question as to how you'd actually control this gravitational wave telescope. You'd have to move your spacecraft around in order to pick up the light that you would want. It may even rely on serendipity, that you would just look as the spacecraft travels away from the sun. You look back at the sun. Of course, you've got to block out the disk of the sun with something called an occulting disk, and look at the ring of light around it. But that ring, as you decompose it into a point image, that you might pick up things serendipitously rather than being able to aim it at anything. But there would be certainly some choice put into what direction you send this spacecraft into to see suitable targets on the other side of the sun. I'm not explaining this very well.
No, it makes sense. Because we're talking 40 or 50 years before potentially launching such a mission, and by then Canon will have invented a digital camera that can do the same thing. So.
Maybe so. Yeah, the computing power. You put a quantum chip into your camera and it'll do it for you.
Yeah, I reckon. At the moment, I can't use my digital camera on my telescope, not my little one. I can use my big SLR, but I'm going to solve that problem. I reckon if I can work out a way, I'll get some really good shots with that camera, because it's actually a much more powerful camera than my SLR, my little digital. But that's another problem, telescopically speaking. But yes, all right, watch this space. 40 or 50 years' time, we'll let you know whether or not that mission is a go. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Rightio, time to answer some audience questions on Space Nuts this week. We've got one audio question, one text question, and a nice little message. But we'll start off with an audio question from one of our regulars. It's Rusty.
G'day, Fred and Andrew. It's Rusty in Donnybrook. I want to ask Fred about an instrument which must be exciting for him. It's the micro shutter on NIRCam on the Webb Telescope. They say it can be used to isolate a distant galaxy from those around it, so for spectroscopic analysis. And I'm wondering what other uses this instrument can be put to, and whether there are analogous instruments on ground-based telescopes. But I'm just wondering if things like isolating small parts of a nearby galaxy can be used to do a Doppler analysis across the galaxy, so we can look at the different speeds relative to us at all different parts of a galaxy. Things like that. So really interested in finding out what Fred thinks of this instrument and what it might be useful for in infrared light.
Thank you, Rusty. That's straight out of the Geek Handbook, that question. Seriously.
Let me answer the last bit first, because we already do that kind of, that kind of observation of galaxies. We use IFUs, which are, that's a tough. What's an IFU again? It's an image.
I'm not sure I can say it out loud, to be honest.
These are devices. We use optical fibers for this.
Yeah.
So if you imagine a bundle of optical fibers all placed in contact, and you slap that on the image of a galaxy, then what you're doing is you're allowing every bit of that galaxy image to go down a different optical fiber, and at the other end you can spread them all out into a line, and you get a spectrum from each one of them, and so you can analyze in great detail the basically the layout of the structure, the velocity structure in particular, of what's going on in the galaxy. And that's a huge part of the work of the Anglo-Australian Telescope, which has basically done surveys of exactly this kind. The new instrument that does all that stuff is called Hector, and it's a multi-IFU spectroscopic camera. So the kind of science that Rusty's referring to is already stock in trade, and at infrared wavelengths, it's not that much different from what it is at optical wavelengths. It's actually not so easy to use fiber optics at infrared wavelengths, because the fibers themselves tend to be warm, and so they radiate, infrared into your detectors.
Yeah.
But just going specifically to the instrument that Rusty's referring to, it's actually on
micro shutter.
Yeah, the micro shutter. It's on their near infrared spectrograph, or NIRSpec. There might be one on MeerCam as well, but NIRSpec is the instrument that is closest to my heart in that regime. What's a micro shutter? Well, it's an array of tiny windows, and these windows are 100 by 200 microns. So 100 microns is a tenth of a millimeter.
Right.
So you immediately get the impression that these are very, very small windows, but the trick is that they can all be closed with a shutter, which can be individually addressed. So you've got these, well, in this case, 250,000 windows, each with its own shutter that can be individually addressed. So you can open and close them in any way you want. And if you place that in the focal plane of a telescope, like JWST, which is what we're talking about now, what you can do is once again isolate certain parts of the image field.
It sounds like a fly's eye.
It is a bit like a fly's eye. It's rectangular rather than kind of hexagonal like fly's eyes are. And unlike a fly's eye, you can open and shut each element of it at will. And that's really the extraordinary part about it. It's technology that's actually been around for quite a while, because even when I was working on building multi-fiber instruments, you could buy, not in any sense quite such high resolution. In other words, 250,000 of them, but you could buy micro mirrors, which are the same sort of thing. But instead of opening a little shutter, what you do is you tilt a mirror, a tiny, tiny mirror. So you've got an array of several thousand of these mirrors, each one of which can be tilted individually to deflect the light. So you can steer the light away from your detector. So it has the same effect as the shutter, but it's in reflection rather than in transmission. As I said, it's that technology has been around for quite a while. But this, I think, is a highly refined version of it, the micro shutter array on the Webb Telescope. It's going to be fabulous to see what kind of science it will produce. It's exactly the sort of thing that Rusty was talking about, where you want to isolate different bits of of a galaxy, for example, to look at the spectrum of each of those bits individually. And much has already been done in that field with instruments at the Anglo-Australian Telescope and elsewhere. So great stuff, and we look forward to what it can produce.
Yeah, it makes me wonder what else is on the James Webb Space Telescope, in terms of gizmos and little pieces of technology. It must have quite an array.
Yes, indeed, that's right. And we will, as time goes on, I'm sure, focus on these different instruments because they'll produce significant results. So watch this space for the kind of kit that we might be talking about in the James Webb Telescope's marvellous work.
My favourite's the Viewmaster. It's a real ripper, that.
The stereo view. Did you have a Viewmaster?
I did.
Yeah,
I did.
I never had one, but I always wanted one.
It sort of got me. I've sort of been a bit nostalgic lately on the radio because I do a little segment about historical local news. So I get newspaper stories from this day in history. And there was a story in today's local paper back in 1954 about a marbles competition that was being held at the school. It was a championship. Nobody plays marbles anymore. But I used to play marbles at school all the time, I just came across that story and thought, oh wow, this is going to dredge up some memories. I'd never play for keeps though, because I didn't know I was
there you go.
Too much of a coward. Didn't want to lose all my marbles. Boom, boom.
I won't make a comment there, but you probably still got your bag of marbles somewhere.
They'd be around. Yeah, they would be around.
Yeah,
I had quite a collection. Cat's eyes and bonkers.
Bollies were the ones
Bollies, the big ones.
Yeah, the big ones.
You call them. We called them bonkers.
Oh, bonkers. Okay, Bollies in Britain.
Oh dear. That's beside the point. But it just sort of popped into my head as we were talking about other things. Now, let's. Thanks, Rusty, for your question. Let's go on to a question from Gingy Anvik, who actually sent this one on social media, I think. He says, I was reading up on various galaxies and came across this article from 2010 about the discovery of a weird radio source emanating from the core of the starburst galaxy M82. It seems it quite abruptly turned on between two observations spanning only a week back in 2009. It didn't really seem to resemble anything recognisable by the researchers, and the conclusion of its nature was as of then unknown, not known. From what I could understand, their favourite hypothesis was a microquasar, but I haven't been able to find any updated info on this. There are also many things here hard to wrap my head around, but what really baked my noodle was the part about the apparent subluminal sideways motion of the source. I would love to hear if you can find an update on the nature of the source and if you could explain how things might appear to have subliminal or subluminal motion. It would make me a very happy nerd indeed. And he sent us an image of the actual Galaxy M82, which is causing him headaches. He reckons very frustrated with it.
Yeah. So let's get it straight, Andrew. It's superluminal motion that we're talking about, not subluminal.
Oh, it is too. Yes. Yeah. So I'm inverting my P's.
Yeah. No, that's all right. Look, in terms of the results from M82, the galaxy that Gingy is talking about, I haven't seen anything new about that starburst source either. The microquasars are interesting. I don't know much about them, but the sort of the flagship microquasar, I guess, the one that really gave rise to the term, is an object called SS433, which I remember well from the 1970s when it was first discovered. It's a curious object that's spitting stuff out at a significant fraction of the speed of light, and probably is caused by, I'm not sure whether it's a black hole or a neutron star, but something is gobbling stuff up, and because of magnetic fields is spitting it out along its poles, which we've often talked about before in terms of quasars. And this stream of material has a wobble in it, and that was what made SS433 so interesting. It was really the object that everybody was talking about in, I guess, about 1978 or a bit earlier than that. And still observed. In fact, there's a global what's it called? Global Space Watch, I think, which is a network of small telescopes which are dedicated to observing SS433, and they're all situated in schools around the world. Andrew, there's one here in Australia observing SS433. So it might be an object like that is in M82. But just turning to the other side of Gingi's question, the bit that bakes his noodle is the superluminal motion, which is motion that appears to be taking place faster than the speed of light. That's why it's called superluminal, faster than light. And it's actually a kind of interesting optical illusion. It's relativistic because it only occurs when things are traveling at almost the speed of light, very near the speed of light. But I'll try and describe it as a word picture.
Okay.
So I'm going to wave my hands probably. So imagine that we are looking at a distant object that spits something else out, and that's kind of what's happening with a quasar. There's a blob of material comes from it. Now, if you have no information other than what you can see sort of projected on the sky, all you're going to see is this the central object and a blob of material which is moving away from the central object. And if you know how far away that object is, you can calculate how fast that material is moving. Mm-hmm. So that's fine. But if you now imagine that blob of material is not being spitted out or spat out at right angles to your line of sight. In other words, it's not being spat out sort of across the sky, but it's actually coming towards you as well. Yeah. So it's got, what you might call one component of its motion is coming towards you, and the other is going across the line of sight. So it's tilted. The direction of motion is tilted towards you. What that means is that as this bright object radiates light towards you, as it gets further away from the central object, its light travel time to Earth is less, because as well as going out from the object and apparently across the line of sight, it's also coming towards you, and there's a shorter light travel time when it gets to any particular point away from the central object. And what that does is it means that you see it in its position sooner than it ought to be, because it's come closer to you. So the light travel time shorter. You see it sooner than you ought to be seeing it, and it looks as though it's moving away from the central object faster than the speed of light. That's how it works. I'm sorry I haven't explained it well. You're shaking your head.
Well, I can understand why Gingi's got a headache.
Yeah. But if you think of looking at it from the side, you've got us on the Earth on one side, you've got an object a long way away, and that object's squirting something out, but it's not squirting out at right angles to the line of sight. It's squirting something out towards us, and as it gets nearer towards us, it means that the light reaches us sooner because of the shorter distance that it's got to travel, because it's nearer to us. And it's that bit that makes it look as though you're traveling faster than the speed of light. That's probably the worst possible explanation of superluminal velocities.
So it's
the best I could.
It's an
do without a
illusion of
diagram.
effect.
Yeah, it's an illusion.
Right.
They're not travelling faster than the speed of light because nothing can.
That's right.
But it's an illusion. It was going to be, actually, I've mentioned Stargazer once already in this show, but when I was thinking about that book, I wasn't going to write about telescopes at all. I was going to write about cosmic illusions, and the superluminal velocity was going to be one of the starring cosmic illusions in the book, but it never saw the light of day.
Boom, boom. Oh, we've had a few boom, boom jokes this week.
Yeah, they're all right.
Gingy, hope that helped.
He doesn't look convinced, Gingy.
Well, we had a crack.
Yeah, we had a crack. You need a diagram, that's it.
Yes. Well, I found one on Wikipedia, actually.
Yeah, don't look at the Wikipedia one because it's followed by dozens of equations.
Yeah, I can see that. That's where I stopped.
Yeah.
All right. One final thing before we wrap up. I just wanted to pass on a little bit of feedback we received via Instagram from Jordan. And this is lovely, and we don't actually hear from a lot of people directly, but it's nice when we do. I wanted to send a quick message and just thank you to and everyone in the background, that's Hugh, for dedicating the time to Space Nuts. What a great podcast, 3 exclamation marks. I work in the greater aerospace industry out of US Space Command in Colorado, and I will forever share your amazing show with my colleagues here. Congrats on 300. 301 is in my ear now. Thanks again. Keep up the great work, Jordan. That is lovely, Jordan. Thank you so much for sending us that note. We're kind of, we're humbled by that. It's nice to get a bit of direct feedback from time to time, and we're so pleased that you enjoy the show and that you're spreading the word, and that is fantastic. Just wanted to say thank you for the note. Nice, wasn't it?
Yeah.
All right, time to wrap things up. Fred, by the way, if you want to get in touch with us, you can do that via our website, spacenutspodcast.com or spacenuts.io, and just send us an audio question or an audio message, or you can do a text version as well. Is the AMA tab up the front, up the top, or send us your questions button on the right at spacenutspodcast.com or spacenuts.io. And Fred doesn't know this, but Hugh and I have been talking about the possibility of video questions going forward. We're looking into that, so we get to see your ugly mugs. That'll be good. I'm sure they're not as ugly as ours. Fred, we'll wrap it up. Thanks again.
Great pleasure, Andrew. Always good fun.
Indeed it is. That's Professor Fred Watson, astronomer at large, part of the team here on Space Nuts, and we'll catch up with Fred again next week. Thanks to Hugh in the studio. And from me, Andrew Dunkley, thanks for listening and or watching, and we'll catch you on the very next episode. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
And we're out. And thanks everybody for watching. If you caught us live, we'll see you again next week sometime. Not sure. We'll let you know. Just wait for it to pop up. Hooroo.